looked at in the last two sessions, 2 weeks ago, was looking at things like gender versus age, looking at the relationships between nominal variables, or categorical variables, if you like, things where you can't really put them into any particular order, but you can at least count how many you've got in the various categories. And we use chi-squared and cross-tabulations as ways of analysing that relationship. Then last week, I looked at the relationships between two scale variables, where you've actually got measures of some kind. They are clearly in order. You can use it with various kinds of ordinal scales, but also other kinds of measures you can use. Height and weight is an obvious one to look at the relationship between those two variables. And we use scattergrams and the Pearson's R to look at the correlation coefficient, to look at those relationships. Now, I know one or two of you have been confusing those two. If you start to try to do a cross-tabulation on variables like height and weight, you'll soon know you've gone wrong, because you'll get huge cross-tabulations with loads, thousands of columns and rows and so on. Huge tables that you can't possibly make any sense of. And of course, a lot of them will have expected frequencies less than 5 as well. So that's a good clue that you've done something wrong. Now, remember what I told you in several occasions before, that SPSS does what you tell it, even if it doesn't make any sense. So if you make a mistake and something like that happens, it's because you've made the wrong choice of variables. And in fact, what you should have been doing is probably looking at a correlation and a scattergram and using this kind of approach. What I'm going to be doing this week is actually combining those two things together in some way. So how do we look at the relationships between not just categorical or nominal and another nominal, and not just scale versus scale, but what about if we've got one variable that's nominal and another variable that is a scale? How do we look at the relationships there? And that's what I'm looking at this week. So it'd be a way of looking at, for example, gender versus income. Gender is a categorical variable, a nominal variable. But we want to look at how that relates to income, and income is clearly a scale variable. It's a straightforward measure of income. So how can we do that? And that's what I'm going to be looking at today. How, in particular, what statistics we can use to do that. Okay, just a reminder, because we need to have this in mind about what the difference between the IV and the DV is. I said this in an earlier session, but this is just to remind you. The IV, the independent variable, is what makes a difference, what has some kind of effect, or some kind of causal effect on the outcomes, and is responsible for the differences in the other variable, which is the dependent variable. So the independent variable is the one that's independent, very often independent. We might move it around and we might be able to change it, but in terms of its effects, it has an effect on the other variable. And the other variable is called the dependent variable. That is which is dependent on other things. So in this case, whatever that variable is, its value, we hypothesize, is dependent upon the independent variable. So the very simple example I started with, gender versus income, which is which here? Well, gender is the independent variable, and clearly is independent in this case because we can't simply change gender. I know you can have gender reassignment and so on, but you can't do that for the purposes of research tests and so on. So in effect, it is not changeable. It's independent of us completely. But what's more, we're hypothesizing that gender is making a difference to income. So income, therefore, is the dependent variable. Okay. So what we're doing here then is investigating the effect of gender and income. So in other words, we're saying simply, do men earn more or less than women? And that's the simple way of putting it. But the more complicated way that we have in statistics is the independent variable of gender affecting the dependent variable of income. Okay, now of course this goes back to the null hypothesis. Remember that in statistical tests we're measuring the probability of rejecting the null hypothesis by mistake. In this case, in other words, when we're looking at the effect of a nominal variable like gender on a scale variable like income, then the null hypothesis is no difference between the groups. So the null hypothesis here is, in the case of gender, for example, would be there's no difference between men and women in income. So that's the null hypothesis. And so the statistics we calculate tell how likely we are to get that, how likely it is to be true given the results we got. And when we get a low probability, when the probability we find is less than 0.05, we reject the null hypothesis, and we therefore think we have evidence that there is a difference. And in this case, difference between men and women, for example. And we say we have a statistically significant difference between the two groups that we're comparing. Now, what that difference is, the test doesn't tell us. Again, we need to go back to the results, just as we had to for correlation and for cross-tabulations. You have to look at the results to know what that difference was. The test tells us there is a difference between men and women, but the test doesn't tell us whether women are earning more than men or less than men. To know that, you have to look back to the actual results. And what we do is look at the means. We can look at the mean for the salary for women, the mean for salary for men, and see that. But the test itself doesn't tell us. It just tells us they're different. And that's all, if it's significant, that is. Okay, so let's look at a slightly different example. This is going back to the data set I've used several times, a very simple data set, but it illustrates the point. This is the health and illness group, and I remember I had data about whether they were under 21 or 21 and over. So this is their age categorization in a sense. I'd recategorize it into those two groups. So I've got two groups, the young group and the old group, if you like. And I can look and see whether these two groups differ in the number of, let's say, GCSEs they had. So I can see the differences between those two groups. You might think that maybe they do have different, maybe, I'm not sure which way around it is. Maybe the younger people had more, maybe the older people had more, who knows? We can see. And to do that, we use what's called the independent samples t-test. So that's the statistical test that enables us to judge whether we have got a statistically significant difference or no difference at all, whether we can reject the null hypothesis or whether we have to accept the null hypothesis. So the t-test is used here. The t-test is limited in that it can only look at the comparison of two groups. If we've got three groups, so if you've got people coming from different towns, people from Bradford, Huddersfield and Leeds, then you can't do a t-test on that. You need another test, and we'll come back to that later on using analysis of variance. But if you've just got two groups, and we often do have just two groups, and like we've got here with age, then the t-test is a perfectly adequate test to look at that. Okay, so what do we do? If we do it in SPSS, this is what we've got, and I'll show you in a minute how to do it. I've got a little video to show you how to do it, but for the moment, this is what you get in the output. I hope you're becoming familiar with this now from doing things in the labs. You'll begin to recognize the format of an SPSS output. So I've asked the question, here's my hypothesis, do the under 21s have more or fewer GCSEs than the 21 and overs? And what I've found is, here's the summary tables. This is where it's actually telling you, in the light of the actual data, which has got more and which has got fewer. And we can read this up. You can see the line at the top, the number of people who were under 21. There were 16 of them, and their mean on the number of GCSEs was 6.44. And then below that, the next line, the 21 and over group, there were 18 of those. And the mean value of GCSE they had were 4.28. So the older students had fewer GCSEs than the younger student. Now, is that difference significant? If we were drawing these samples at random from a large number of classes of this sort, large number of different student groups, would that be evidence of a difference between older and younger students? That's the question we want the t-test to help us answer. So our null hypothesis is that there is no real difference between the two groups, but we have got a real difference between the groups we've sampled here. So in our sample, there's a real difference. But is it likely that that's true of the whole population from which we're drawing our samples? And that's what the t-test will tell us. And here's the results you get from that. Sorry if this is a bit small. I've enlarged one bit, the middle bit I've enlarged. But what we have to do here, and it's slightly complicated here by the fact that we have to be careful about whether the two groups, in this case, the two groups are the 21s and the under 21s, and the other group is the 21 and overs, the two age groups. We have to be careful as to whether those two groups have similar variances or not. Variance, remember, is a measure of how much they differ from each other. So do the scores, the number of GCSEs in one group, are they different from each other to the same degree as the number of GCSEs held by the other age group are different from each other. Now, so we measure that by looking at the variances. And in fact, we don't have to do that. We have a statistical test that does that for us. It's testing to see whether those two variances are different or not. And that's what these first two columns here are showing. It's actually, if you can't read it, it says the Levene test for the equality of variances. And in this case, the figure that's appearing, ignore the F number, this figure here is 0.689, which you probably can't read from halfway back. But 0.69, as you probably hope you know now, is way beyond the alpha value 0.05, and therefore there is no reason to reject the null hypothesis. Now remember here, the null hypothesis is there is no difference in the variances. So we're assuming, therefore, in this case, there's no evidence to reject that, so we can say we can correctly assume equal variances. So no significance in the Levene test, assume equal variances. On the other hand, if that figure, that significance was 0.02, for example, then we would have evidence for a difference, and we'd have to use another test which will show us what happens if we don't have equal variances. So there's a first check when you get the results of t-test, check that you've got equal variances. Very often you do. In a lot of cases, that's fine. You have equal variances, you can use that. And the difference comes in the two lines in this output. Now, I wanted to enlarge the middle ones because the next two columns are the actual t-value and its significance, its p-value, if you like. So you can see there's the t-value, degrees of freedom, and there's its significance. And there are two values here. This is the one you would use if the Levene test told you that the variances were not, or there was evidence that they weren't equal. You could reject the null hypothesis. But we have got evidence that they're actually equal, so we use the first number. So equal variances, choose the first number. And it's pretty obvious. You can see it here. Equal variances assumed. There it is, first line. Equal variances not assumed, second line. So, okay, we've got one where they're equal. So we've got the value of t of 2.082. And looking over to the right, the significance is 0.045. So we can say pretty conclusively that that's below 0.05, and therefore we have evidence to reject the null hypothesis. The null hypothesis in this case is no difference between the two groups, the age groups. So we have evidence that the groups are significantly different from each other. Okay, so in this case we have a positive result showing a significant difference between those two groups. Now, just to remind you again how to write that up, how to interpret it. The bit in black is you definitely need. The grey bit is probably useful to have as well. So first of all, we say what the stats were. Students under 21 in the health and illness class, on average, had more GCSEs than those 21 and over. So that's a very rough explanation of the actual results for that sample, that group. This difference was statistically significant, and then in brackets, the actual stats, t equals 2.082, 30 degrees freedom, and p is less than 0.05. And then you can actually go on then, if you want to say more accurately what the actual values were, which is where I started from. The under 21s had an average of 6.44 GCSEs, and those 21 and over had an average of 4.28. The important thing to emphasize here is not just simply to quote the statistic. The statistic tells you only that you've got a significant result. It doesn't tell you what the result is. So you need to either say what I've said at the first sentence here about the differences, or add on, or instead put what I've said here at the bottom as well. So that's how you report the t-test. Okay, so another thing to bear in mind, which I mentioned very briefly last week, was that we also need to be careful that the variables we're using are normally distributed, just as we had to do in the case of correlations. And the t-test relies upon the data being normally distributed. In this case, the number of GCSEs being normally distributed. And the simplest way to do that is produce a histogram to look at the chart and see, does it have that bell-shaped curve that we're looking for in a normal distribution. But you can also use a statistical test for that as well, which you might want to use. If you're a bit doubtful about it, perhaps use a stats test to see whether that assumption about the distribution being normally distributed can be accepted or not. So here's what we do, and this would be true, the same test you do for, if you're doing correlations, you want to decide whether to be parametric or non-parametric, as you would do for the t-test, and indeed for the test I'll talk about later on, the analysis of variance test, where you can compare more than two groups rather. So you use the same tests. It's a bit complicated, and there's some dispute about this as well. That's why I say go back to look at the charts, look at the histograms, because often you can judge pretty well what's going on from those, rather than relying on the tests. There is debate amongst statisticians even about whether these tests are appropriate or not. And some would argue you don't need one, you only need the other one, and it's not very good when you use it here and so on. So beware of that. I mean, you may want to use it, of course you can use it, follow the recipe I've given you here, and use that as justification for choosing either parametric, the t-test, or its non-parametric equivalent. But also, I think I'd like to see you look at diagrams and talk about the actual distribution, what it looks like as well. Put simply, there are two tests you can use here. One is used when the number of individuals in the sample, in the test, is less than 50. Sorry, greater than 50, beg your pardon, I'm misreading it. N is greater than 50, use the Kolmogorov-Smirnov test. And if N is less than or equal to 50, use the Shapiro-Wilk test. Both are done automatically. When you go into SPSS and do this, it'll do both for you, and you just simply choose which one you want to look at. The null hypothesis here is that the data are normally distributed. So in other words, there's no difference between the distribution you've got and a normal distribution. So that's the null hypothesis. So if the probability, when you do this test, if the p is less than 0.05, then the data are significantly different from a normal distribution, and therefore you should use non-parametric tests. So p less than 0.05, use non-parametric. Otherwise, if p is greater than or equal to 0.05, then you use parametric tests. So remember again, the null hypothesis is no difference from, in this case, no difference between the distribution you've got and the normal distribution, and if it is significant, then there is a difference. So you use non-parametric. Okay, I'll show you this in the video. But, as I said, just to reinforce that point, checking for normality, produce the histogram of the dependent variable, in this case, the number of GCSEs in my example. And there is a tick box when you choose to do the statistical text. One of the tick boxes you get in the options is to produce that histogram, and that's a good idea to tick it and do that, interpret the results. Okay, so let's have a look at how to do that. So what you need to do, first of all, in SPSS is identify your two variables. What are you going to be used to group to create the two groups? That will be gender or sex, whatever you've called it. And also, remember this second stage. It's very useful to have a pad and paper to write it down. You need to remember what the values are to tell SPSS what the two groups are. Now, and I'll say this again in the video, it seems obvious when you've got gender, it can either be male or female, and that's it. Why do I need to tell SPSS there are only two groups here? Well, the fact is that in SPSS, you can use variables with more than two values and just pick the two that you want to compare. So it allows you to do that, and it doesn't know that your variable actually only has two values. It just assumes that there can be more than two. So you have to tell it what two values to use, even for a variable that only can have two. But certainly if you have a variable that has more than two, and you might even have one using gender, so you might say male, female, not known, something like that. In which case you'll have three values, and you'll need to tell SPSS that 1 and 2, or 0 and 1, whatever you've done, are the two values to use. So it might be 1 for female, 2 for male, or it might be 0 for male, 2 for female, whatever you've used, you need to remember that. Then select Analyze, Compare Means, Independent Samples t-test. I'm sure you're getting used to using the Analyze menu now. It's comparing the means of the two groups, and we use Independent Samples t-test to do that. And let me show you the video now. Okay, so how do you write up the results for that? In this case, it was no reason for rejecting the null hypothesis. There was no evidence of any difference between the two groups. So we say that. There is no evidence that the mean cholesterol level in month 1 for women, which I've given the actual figure here, is different from that of men, and the figure for them. and then the t-test values below that. T-test equals 0.270, degrees of freedom 48, and p equals, I've actually given the accurate figure here from the SPSS output, or you could simply say, p was greater than 0.05. Okay, what about if it fails on the test for normality? What's the equivalent test of a t-test if you've got data that aren't normally distributed? How can you compare the two groups in that case? Well, the test we use is called the Mann-Whitney U test, and it does exactly the same thing as the t-test, but it's slightly more cautious. It takes into account the fact that the variables, the dependent variable, is not normally distributed, and gives you a slightly more cautious set of statistics on the basis of that. And it works exactly the same way as the t-test. Perhaps I'll show you that now. It's only a very short video.